Hello, everyone on the other side of the internet, and thank you for having me. Thanks to the Palomar Observatory for inviting me. Part of our job as astronomers is to reconstruct the history of the universe and to understand our place in it. In the spirit of telling stories of the universe, this talk is broken up into three stories. The story of a pair of black holes, the story of a supermassive solitary black hole, and the story of us from our beginnings and how those stories are intertwined. We're going to take a chronological approach to tell each story as they unfold in parallel and see how they come together in the end. Before we begin our first story, there are a couple things I want to tell you. The first is to provide a reasonable context for putting together our timeline of events. This is the galaxy in which we live, the Milky Way, and our best reproduction of its shape. It is a spiral galaxy with two major arms, the Perseus arm and the Scutum Centaurus arm, a few more minor arms, and a bar across the center. Extending from one of the minor arms, the Sagittarius arm, if I can get my laser pointer and put it up here. So here's the Perseus arm, there's the minor Sagittarius arm and the little Orion spur coming off of it right there. That's where the sun and the solar system are located. The sun takes about 240 million years to go around the galaxy. So I'm going to call that 1 Milky Way year. In that context, the sun and the solar system is 18 3/4 Milky Way years old, and the entire universe is 56 2/3 Milky Way years old, according to our current best measurements. Our first story is going to start 48 3/4 Milky Way years ago. So we're going to back up time here. It's going to go very quickly. We're going backwards in time. There we are. So we're actually here because we did an integer plus 3/4 of a turn. All right. The second thing I want to tell you as our first big story begins to unfold is about the evolution of stars. This is a nice storyboard of how different stars evolve over time. Stars all begin their lives by fusing hydrogen, the lightest element, into helium, the next lightest element, releasing energy in that process and supporting themselves against the pull of gravity. Stars of medium mass, like the sun, will fuse all the hydrogen in their cores to helium. The core will collapse under gravity, heating up and then reaching a sufficient temperature to start fusing helium. The outer parts of the star will swell up to giant-sized proportions due to the additional heat. The most massive stars have a much shorter story. Since they are more massive, they have more gravity and they have to fuse their hydrogen at a much higher rate to support themselves. These stars will also fuse helium into elements like carbon and oxygen, then to magnesium, silicon, etc., until they get to iron. They will attempt to fuse iron, but that process won't release energy, leaving the core unsupported against gravity. The cores of these stars collapse into a point called the singularity, surrounded by an event horizon, which is a region of space around the singularity where gravity is so strong that light cannot escape. This is a black hole. And with that, we begin our first story. 11.7 billion years, or 48 3/4 Milky Way years ago, that's 30 Milky Way years before the sun formed. In a galaxy that is currently 1.2 billion light years away, two extremely massive stars formed in orbit around each other. The exact location of this galaxy is a bit uncertain, but most likely it resides in a direction similar to the Large Magellanic Cloud, in the southern hemisphere and below the plane of the Milky Way. So that's as shown in the on the right with these colored contours. So there's the Milky Way band, and these contours are outlining where we think that galaxy was or is. This pair of stars, called a binary, has a total mass of 156 times the mass of our own sun, with one of them shown in yellow on the left side graphic, nearly 60% more massive than the other. The more massive of the two stars evolves more quickly, finishing its hydrogen fusing stage in only 3.5 million years. That's 0.01 Milky Way years. By comparison, our sun will take 10 billion years to use up its hydrogen. So its core begins to collapse under gravity, heating up. The outer parts of the star swell up due to the heat. And this is where the binary aspect becomes interesting. The first star swells to the point where gravity from the other star is able to siphon material away. In this process, the first star loses about 50 solar masses in all, with about half of that, 25 solar masses, transferred to the other star. It is still nearly 42 times more massive than the sun, and the helium fusing phase goes by in a stellar heartbeat, less than 300,000 years. The remaining stages go by even more quickly, and the core eventually becomes too compact to be supported by anything against gravity. It collapses, forming a black hole, and the outer layers are blown off in a supernova. Meanwhile, the other star is continuing to fuse the hydrogen in its core, but will also quickly end that, taking only 5 million years instead of the 3.5 million years in the case of the first star. When the second star ends its hydrogen fusing phase, its core collapses, heating up to the point of fusing helium, and the outer layers swell up due to the increased heat, as the first star did. However, due to the lower overall mass of the system, the star expands to encompass both objects. The core of the second star begins to evolve similarly to the first star, and friction causes the orbit of the two stars to decay quickly. Over the next 300,000 years, the separation between the two stars shrinks by a factor of nearly 90. The second star evolves to shed its outer layers, leaving behind just the core. And then it too collapses to form a black hole. Over the next 43.75 Milky Way years, about 10.5 billion years, the dance of the black holes continues largely uninterestingly, except that the orbit very slowly decays due to the loss of energy in the form of gravitational waves. More on that later. Meanwhile, in our own galaxy, 30 rotations pass, corresponding to 7.2 billion years. There's the 30 rotations. And our second story begins. A giant cloud of gas is chilling out, not knowing that it is about to have an eventful day. On this day, a nearby star reaches the end of its life, with a final collapse of its core, and the explosive shedding of its outer layers. The resulting shockwave slams into the unassuming cloud, compacting it, and therefore increasing its gravity. That increase in gravity is enough to fragment the cloud, with each fragment collapsing to form a star, one of which is our sun. Not all of the fragment goes into forming the sun. A tiny part of it, which starts with a tiny amount of rotation, as the fragment collapses, begins to rotate faster and faster, just as a skater does when she starts spinning and then brings in her arms. That tiny part forms a disk, since the collapse preferentially happens parallel to the rotation axis, this way. The so-called debris disk itself begins to fragment as particles start sticking to each other to form larger and larger and fewer objects, i.e. like planets and moons and asteroids and other denizens of the solar system. The incidence of collisions continues to decrease as fewer and fewer separate objects persist, but that process of collisions never really goes away. For the third object from the new sun, one of the last major collisions is with a Mars-sized object, which we call Theia, resulting in the formation of the largest moon among the inner rocky planets. Of those rocky planets, only Mars also has moons, which may be captured asteroids. Another curious thing seems to happen about 600,000 years later. That's about 3 Milky Way rotations. So let's go 3 rotations here. We can trace the incidence of collisions as a function of time using the moon's surface and the cratering history there, which reveals an asymptotic decline as expected, except for a spike around 3.9 billion years ago. One possibility might be, as we have now observed in other systems, that Jupiter shifted its orbit, which then perturbed a bunch of asteroids, sending them careening into the inner solar system. On Earth, it is in the aftermath of this spike that we see the earliest evidence of life and fossils. During this period of Earth's history, we see the Archean Eon featuring the development of single-celled life and photosynthesis, segueing to the Phanerozoic Era, featuring the stabilization of the continental plates. Incidentally, during this time, the moon is closer to the Earth than it is today, and the Earth was rotating faster, only 20-hour days. During the middle of the Phanerozoic Eon, we see the rise of multicellular life, which brings us to about 1.2 billion years or 5 Milky Way years ago. So we're going to get here. So now we are here, only 5 rotations left until we get to the current era. At this time, in the galaxy from our first story, something monumental is about to happen. Those black holes have been orbiting each other for quite a while, and the orbit has been decaying due to the shedding of energy as gravity waves. As the orbits get smaller, the black holes go faster and faster in their orbits. In the final moments of this orbital decay, the black holes are orbiting extremely fast. The black holes get close enough that their event horizons, the distance at which the escape velocity is the speed of light, overlap, and the black holes merge. 6, 5, 4, 3, 2. It's slowing down a lot here. 13, 12, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Boom. As we zoom back out, we can see the gravity waves, ripples in the fabric of space-time traveling off. I'm going to pause it right if I can. No, it won't let me. Why not? All right, laser pointer off. Let me go back here. A little bit right there. Yeah, that's a good place. Notice that the waves at the very end pre-merger, that were these guys right here, are a lot more compact, a lot more tightly spaced than the ones way out here that were emanated before the merger. Okay, the merger happened about here, and then we had this ring down period. Okay? So we have larger amplitudes as indicated by the larger, the more intense colors here, as opposed to the more fainter colors here, the more muted colors there. So notice that the waves are very tight and have larger amplitudes than when the black holes were farther apart. So if you were standing off somewhere to the side, your space-time as you would measure it would look something like this form down here. And that's what was simulated, that's what was predicted. From here, we enter the Phanerozoic Eon of Earth's history, which we are still in. This period comes with an explosion in the diversity of life and features my 7-year-old's favorite animal ever, and who can blame her? Dinosaurs. Dinosaurs lived during the Mesozoic era, which starts around here 252 million years ago and goes until about here 66 billion years ago. Who knows how long they may have gone had it not been for a cataclysmic event, which is the KT extinction, brought about by an asteroid hitting the Earth. We actually see evidence for this impact in the Michelson crater on the south side of the Gulf of Mexico. So here's the Gulf of Mexico here. Let me get my laser pointer back so it's easier to see. So here's the Gulf of Mexico here. There's the Florida panhandle there, Mexico here. You see this little red box here. That's what's shown in this large image here. This white line here is the coastline of the southern tip of Mexico that you see in that red box there. So you notice that there's this nice little circle delineating small changes in gravity. So this is all telling us about changes in gravity on a 1 milligal level. That's 1,000th of our acceleration due to gravity. So that's small changes indicating that there was a crater there. Okay? And there's a further evidence of the crater here in the form of all these sinkholes that are these white dots. You see that forms a nice little circle. So they think they've identified where that asteroid hit, and that's the Michelson crater. About 12 million years after the end of the dinosaurs is where our third story finally begins. On the right, I have a picture of the constellation Virgo with the asterism of the Virgin. Up near the top, there's a galaxy known as M87, the 87th object in a catalog assembled by French astronomer Charles Messier of things that annoyed him because they weren't comets. A Hubble picture of M87 is shown on the left. This is a giant galaxy, elliptical in shape. In the Hubble picture, you can also see a blue jet of material shown in blue. This jet originated down in the heart of the galaxy, where there resides a black hole of incredible mass, about 6.5 billion times the mass of our own sun. The jet, among other bits of evidence, is a hallmark signature that the black hole is having a snap. Matter is slowly spiraling in. In this simulation, one can see a prediction of what that looks like. Notice that there is this ring of light. This is called the photon ring. This is the radius at which light is forced to orbit, which is dependent on the mass and the spin of the black hole. The brightening on the left side is also an indication of the black hole spin. The event horizon of the black hole lies within the dark patch, so the light coming from the accreting material can easily escape, taking about 470,000 years to disembark from M87. M87 is part of a large cluster of galaxies, as shown here. And it's unimaginably called the Virgo Cluster because it's a cluster in Virgo. Each fuzzy blob in this picture is an entire galaxy in its own right. And the galaxies are all bound together through gravity in the cluster. The cluster extends about 10 million light years in front of M87. So the light takes 10 million years to exit the cluster. About 36 million years after that, we see how our three stories are starting to converge. At this point, the two signals, the gravity wave from the coalesced black holes and the light from M87's black hole, enter what is called the local group of galaxies. This is a group whose largest members are Andromeda in the upper left side here, and the Milky Way, shown in the center of this graphic. I'm guessing the artist was probably a very Milky Way centric, had a bias toward us. Each of those galaxies are surrounded by a number of groupies, smaller dwarf galaxies, like the large and small Magellanic Clouds. The photons from the M87 black hole are shown in green, coming in above the plane of the Milky Way, while the gravity wave from our first story is shown in orange, coming in below the plane of the Milky Way. In our journey through time, we now arrive in the Cenozoic Era, which features the rise of mammals after the extinction of the dinosaurs. About 7.5 million years after those signals entered our local group of galaxies, we, Homo sapiens, finally enter the story. 65,000 years ago, both of those signals entered the Milky Way as we began our migration out of Africa. 411 years ago, or 12 years ago at this point, Galileo first trained a telescope on the heavens, discovering that Venus goes through phases like the moon, and Jupiter has its own moons. At this point, those two signals entered the Orion spur of the Milky Way's Sagittarius arm, where the sun is located. At the beginning of the 19th century, the signals were a little over 2 light centuries away. At this point, in the development of human knowledge, Thomas Young demonstrated that light behaves like a wave. By sending light through a pair of slits up here toward a distant screen, shown here, the result was a series of bright and dark features that were spaced periodically. Young was able to explain this by observing that water waves also do this. This is actually a figure from his paper. Sending waves through a pair of slits, that's at A and B, causes the waves to come out emanating in a circular pattern like this. And where the waves overlap, they can add together if they are in sync. So anywhere you see the dark lines crossing, that means the two are in sync. That is, the crest of one wave combines with the crest of another wave, or vice versa, trough and trough. Or in between, they could cancel each other out if they're completely out of sync. The crest of one wave combining with the trough of another wave. So he could predict that the positive contributions of light would travel in certain directions by tracing out where the waves would be in sync. This wave-like property of light provides two immensely important tools that are relevant for humanity being able to detect those signals: high precision measurements of distance and high resolution imaging. In 1865, toward the end of the Civil War, James Clerk Maxwell used the equations governing electricity and magnetism to make a very puzzling prediction that light has a certain speed that he could calculate just using physical constants. This is the only time in physics that a specific speed had been predicted. It begged the question, what frame was that relevant to? If you turn on a flashlight and measure the speed of light as what Maxwell predicted, surely if you started running in the direction of the beam, you would measure something smaller. This was the beginning of the end of Newton's physics, and an opportunity for another famous physicist to make his mark. In 1879, as those signals get ever closer to Earth, a member of the human race was born without whom we wouldn't have known to even look for these signals. There's baby Albert Einstein. No doubt he's pondering the speed of light as the flash from the camera goes off. This question of what frame had the speed of light being the value Maxwell predicted led to our next milestone in 1887. An experiment by Michaelson and Morley at Case Western Reserve University was carried out that would eventually become known as the most famous failed experiment. Here's the apparatus that they used, called a Michelson Interferometer. It relies on light bouncing off mirrors to measure precisely the distance between mirrors. Here's how it works. Light emerges from a source and hits a piece of glass that is half silvered, half transparent, in a way that lets half the light through and reflects half the light at, say, a 90-degree angle. The two beams of light, since they were part of the same beam, are in sync as they travel toward the mirrors. They reflect off those mirrors and come back to the beam splitter, which recombines the beams and reflects them toward a screen. Depending on the relative distances of the mirrors, the returning beams might be in sync or may be completely out of sync or in between. The resulting brightness of the combined beam gives a precise measurement of that relative distance. Michelson and Morley used this device to see if there was a preferred frame for light, as we on Earth moved in different directions through space as Earth rotated, since tiny variations in the speed of light in our frame would change the phase of the returning waves. They saw no detectable changes, concluding, therefore, that there is no evidence to suggest a special frame for Maxwell's predicted speed. This set the stage for Einstein to convince us 18 years later that that speed must be the case in any and all frames independently. The implications of that insight would be far-reaching, leading Einstein to replace ideas that Newton and Galileo put forth regarding measurements of space and time. The apparatus built at Case, the Michelson Interferometer, would eventually also become a tool for high-precision length measurements for detecting gravity waves. In 1915, Einstein followed up on his miraculous year with a publication of his general theory of relativity. This theory led to the prediction of black holes and gravity waves. At this point, the gravity wave from our first story is exactly 1 light century away, and the M87 photons are not far behind. Only at this point do we even have an idea that these even exist and that we should be looking for them. In 1920, Michaelson and Pease used this interferometry technique to measure the diameter of Betelgeuse, the bright red star on the top left armpit of Orion. This demonstrated the use of interferometry to gain a high degree of spatial resolution. That's actually a Hubble image, I think, if I remember. That's not the original one by Michelson and Pease. I couldn't find that one. Our intertwined stories are quickly coming to a climax here. In the late 1960s and 1970s, groups led by Kip Thorne, Rainier Wise, and Barry Barish began to consider building large versions of Michelson interferometers for what would become the Laser Interferometer Gravity Wave Observatory, or LIGO. The initial operations for LIGO began in 1999, but were not yet sensitive enough to detect gravity waves. So we are going to jump ahead to 2009, when Dr. Shepard Dolman and his collaboration conceived of a way to image the environment of a black hole down to its event horizon. This was the Event Horizon Telescope. Contrary to its name, the Event Horizon Telescope is not just one telescope, but many around the world, combining forces, collecting light from a source, and combining them to give them the requisite high spatial resolution to compare to the simulation of M87's black hole that I showed you before. At this point, the gravity wave is only 6 light years away, and the M87 photons are trailing behind by just 2 light years. A year later, the initial operations with LIGO ended, and the installation of more stabilizing suspension systems to damp out noise sources, enabling even higher precision measurements of distance began. The upgrades and commissioning were finished by early 2015. 2 interferometers were built for LIGO, one near Hanford, Washington, and one near Livingston, Louisiana. Having at least 2 are crucial to ensure both consistency and reproducibility of results, as well as providing a means of gauging the direction from which the gravity waves come. And just that happened on September 14th, 2015, at 9:45 Greenwich time. The gravity wave from our first story, having traveled for 1.2 billion years from black holes that had been orbiting each other for 10 billion years before that, long before our solar system was even a glint in the eyes of the Milky Way, passed through the Earth. The waves passed the Livingston detector first and passed the Hanford detector 7 milliseconds later. Both showed exactly the same waveform, confirming a real detection and allowing us to reconstruct its history as presented here earlier in this talk. Not to be outdone, the photons from the M87 black hole arrived 2 years later, as the Event Horizon Telescope collaboration coordinated their worldwide observations on April 5th, 6th, 10th, and 11th, 2017. Their observations not only included the intensity of the light, but also the phase of the wave, whether it was a crest or trough or something in between. They also took advantage of the rotation of the Earth, which allowed the telescopes to sample different locations and the arrival of M87's photons from slightly different vantage points. The volume of data recorded was about 15 petabytes. When we collect data at telescopes, our usual mode of operation is to transfer the data electronically over the internet to our computers at home. If the Event Horizon Telescope collaboration had tried to do that, most likely it would have broken the internet. So they stored the data on hard drives and flew them to the MIT Haystack Observatory in Westford, Massachusetts. The data were processed independently by 3 teams to ensure quality control. This is the final result. While it might look like a fuzzy donut, I want to be clear about 2 things. First, this is the very first picture of the inner region around a black hole that we have ever seen. Up until now, every single depiction of black holes has been strictly an artist's impression or a simulation. Second, while it may seem blurry, this is the highest resolution image ever taken of something in space. The photon ring, that's here, has a diameter of 42 micro arcseconds. This is about 24,000 times better than Hubble can see. This would be equivalent to resolving something that's 0.7 millimeters across, like the tip of a mechanical pencil, from a geostationary satellite above the Earth. Of course, for more details about how they did this and how they put it together, stay tuned in a couple weeks for Dr. Catherine Bowman's talk. I won't steal any more of her thunder. Photons have been coming to us from M87 before April 2017, and they continue to do so now. But these particular photons were part of something extremely special. Similarly, gravity waves have likely been passing by undetected before the demonstration by LIGO. Think of the stories that we've missed. In reconstructing the history of the universe, we still have a lot of work to do. Thank you. I see that there was something in the chat already. Let's see. Where's the chat window? Chat window.
Yes, I was looking to see if there were any questions in the chat. Dr. Ganguly, excuse me.
Mount Wilson Observatory. Yep.
Thank you very much. Let me open the floor to questions. You can turn on your microphones and let's see if we got any questions from anybody. Let me start then. You may have made this point, and I may have missed it, but at what rate do gravitational waves propagate?
So from that 7 milliseconds time interval between Hanford and Livingston, we could actually verify that gravity waves travel at the speed of light, which is interesting.
Yeah, I can't quite figure why that should necessarily be the case.
So the speed of light, as I tell my students and I show them, is nothing particular to light itself. It's a property of anything that propagates that has no mass. So photons, light has no mass. It propagates at that speed. Gravity itself has no mass, so waves from gravity also travel at that speed. That's sort of a special, interesting speed, and that's what makes it so fundamental as something in the universe. So even though Maxwell predicted it using the equations from electricity and magnetism, that speed still refers to anything that has no mass.
And does that come out of? Is that a prediction of special relativity? Of general relativity.
It's a prediction of general relativity because that's where we got the gravity waves from. Yes. But the speed of things with no mass, that's from special relativity. Yeah. Yes.
So I have a question about the two events that you talked about, the black hole collision, the merger of the two black holes,
right,
and the black hole and the singular black hole in M87. Are those just a coincidence, or are they somehow related, those two events?
No, they're completely unrelated to each other.
Unrelated.
But they happen to be, within 2 years. I mean, we've been getting light from M87, even that far back as Charles Messier, right? I mean, he detected it way back then. We've been continuing to see it. But I just selected those particular photons because those are the ones that the EHC collaboration collected at the telescopes in 2017.
Kind of a convenient time scale for human beings.
Yes, right. I mean, it's amazing how the technology has sort of converged like that. Yeah.
Yeah, I have a question.
Do gravitational waves attenuate at all as they cruise through the universe?
I mean, in the same sense that light will get fainter, in that same sense, the amplitude of those waves gets smaller and smaller and smaller, just because they're encompassing a larger and larger distance. Yes, it will. And that's why it required such a high precision measurement on our part If we were measuring this close to the black hole, we wouldn't the pair of black holes. We wouldn't need nearly as sensitive as what of an instrument that we have now.
So if the amplitude of the gravitational wave is decreasing, eventually you'll come to point undetectable, or asymptotically they go to 0 or whatever. Any idea how far that would be?
Well, I mean, that particular gravitational wave was undetectable by us, from the 1999 version of LIGO. So it depends on how good your noise cancellation is, and how well you can damp out noise sources. And that's the remarkable thing that happened in that 16-year time between 1999 and 2015. They were really able to, do wonders with damping out noises and making things even more sensitive, so we could get down to that level. But yeah.
Can I break in at this point? Harry Carlson has raised her hand and asked for record. Harry, you have a question?
Yeah, early in the talk, you just kind of casually mentioned that using iron does not release energy. And I was surprised to hear that. Can you talk a little more about that?
So iron is interesting because it has essentially the most tightly bound nucleus of all the elements. So elements that are lighter than iron, when you fuse them, they will release energy. Elements that are heavier than iron, you have to split them apart to get energy. And so iron is sort of that juncture where that transition happens. So the idea of a fission process versus a fusion process.
Okay. So does it just happen because of the enormous pressure? Is that why iron gets fused? Okay.
Yeah,
Thank you.
It tries, but it doesn't succeed.
Okay.
Right.
And one more, if I could, Cordell Harris.
Now, Cordell, what you guys have to know is Cordell is a student of mine. He just graduated from Flint.
Welcome.
And he always has a habit of asking really annoying questions because they're really good.
Okay, I'll try to live up to that with this one. So, light, as it travels from places really distant from us, ends up suffering from cosmological redshift. Do gravitational waves do the same thing?
Good question.
Okay, so the mechanism for that then must just be exactly the same. I wondered because
it's just the stretching of the universe.
Yeah, I wondered, since gravitational waves themselves are a stretching and pulling, if they did the same thing. But I imagine it's the same as if you had like a sheet of something that you put a wave through and then you stretch that sheet at the same time.
Right. Was there a question, or did you want me to just comment?
Well, I guess the question was that the right way to think about it?
I'm not a complete expert in exactly how gravity waves, how those are generated, but yeah, I imagine it would be something like that.
Okay, cool, thank you.
See, he asks annoying questions that I can't answer, and so that's why I made him graduate, because I have no answers for him.
We had a question in the chat from Roy Gunson. Would the gravity wave be strong enough near the site of the merger to tidally disrupt stars within some limited range of distance, a few light years perhaps?
That's a really interesting question. I don't know. It may be. I suppose that's possible. Depending on how much shear there was.
Okay.
So something from Sandra.
Yes, there was a comment from Sandra.
Yeah. She's a member of the Ford Amateur Astronomy Club. Okay. Yep. Let me take down your email address. Sure.
Thank you.
Sure. Actually, let me do
other questions, please.
Copy and paste. Yeah.
I'd like to return to Tim's question about attenuation of the gravity waves. Yes, they're being attenuated kind of as they expand over space-time, but are there things that they, for example, light waves in the Milky Way are attenuated by dust. When they come to us, they're scattered by dust that intervenes between wherever their origin is. And does this happen to gravitational waves as well?
Well, gravity waves, because it's space-time itself that's doing the waving. So it's not gonna interact with dust in the way that light would, right? Light can scatter off dust and whatnot. So we're not. If I could imagine that, say a cluster of galaxies or something that had a lot of mass, that's something that would then maybe possibly change things.
Is anybody looking for that kind of scattering between these galaxy clusters?
I'm sure there's lots of, in terms of gravity waves, in terms of people looking for like lenses, in terms of people thinking about how clusters of galaxies affect things. Yeah, there's lots of very smart people, much smarter than me, people doing things like that.
And Carrie Carlson, please jump in.
Oh, I was going to ask could two gravity waves interfere with each other from different black hole mergers?
Ooh.
That's a good question. Like light can interfere with each other, right? So if it passes through each other, I could imagine that it probably would. They would pass through each other then, but so
they could
at that
do
instant,
the same thing
right,
that light does. They could line up or they could interfere.
Right. I would imagine.
Okay.
I would imagine so.
An area of zero gravity.
Oh.
Wow.
Well, zero distortion of space-time.
Yeah.
Which is different from zero gravity.
Wonderful thought.
I like it. Sounds like there's a good science fiction story in there somewhere.
Yeah.
Okay, we have a couple more hands raised. Steve Miller, will you jump in?
Steve, you're on mute.
Unmute yourself.
We were talking about a moment ago about the potential. Somebody mentioned something about the equivalent of redshift in gravity, and a lot of discussion we're talking about the waves. And so, does it make sense to think of the wavelength of gravity?
Yeah. Well, so in this case, so let me see if I can back up in the to that slide. Where'd it go? Go here. So if I go back to this slide here, so this, you see these, these are essentially what you're calling the wavelengths. Those waves, those lights are actually caused by the period at which those black holes were orbiting each other. So as they got closer and closer and closer, they were orbiting faster and faster and faster. And so because they were orbiting faster and faster and faster, the wavelength got shorter and shorter and shorter. And that's what the prediction was, and that's what you see here. So that's what you see there.
So we're detecting the spectrum of the gravity waves, essentially.
I suppose you could think of it that way. Yep.
It's going to take a lot.
It's pretty wild. This is a completely new way of observing the universe, and it's so cool. When it came out, I was actually on sabbatical that year, that semester, and I was in my basement just watching the news conference there, and it was fantastic.
Okay, another one. Reza, will you turn on your microphone and jump in, please?
Sure. Hi. First of all, thank you very much for a great talk. Can
you
you
for
tell us
having
more a
me.
little bit? Thank you. Can you tell us more a little bit about the data that they handled at EHT? So I understand they did not build their own telescope, so they had to move the hard drives, as you mentioned, to the location and from there. And then, and afterwards, how did they process that amount of data? What computers they had, or how was it done?
I'm going to defer that question to Dr. Bowman's talk in 2 weeks, because she is the one to answer that question, because she was right there and she did it.
Okay, thank you very much.
Other questions? Other questions?
Question?
Yes.
Mm-hmm.
The wonderful way you compared the time of the event to the archaeological, the geological, the biological, the human history was fascinating, Rajib, and just like compliment you on that, but
Thank you.
Was it a challenge to do those comparisons?
It was. I mean, it was a lot of fun, right? So what's interesting is that my father is a geologist, so I kind of grew up with that. The joke around the house was that my teenage rebellion was going to study things that were far from the Earth as possible. So I studied quasars. But no, it was really, and it was interesting because the first time I gave this talk, my dad actually had a chance to watch the talk, and it was the first time he could actually watch me give a talk of this nature, and he was very impressed, and he liked it. That was very touching to me.
It was very, very nice, because it's very difficult, as you know, to give people who are not into the science and everything a feeling of relevance, and that did it very nicely. Thank you.
Yeah, thank you. See, there was a question from someone calling themselves SDAA meeting, which is gravity waves are a field, but what does...
Robert. Yeah, I was wondering, could you show the slide of James Clerk Maxwell again about where he determined the velocity of light?
Oh, let's see, sure. Let me get that up here. So that was back here. Yeah.
Okay, thank you.
Okay.
I think many of us have gone to school for long periods of time, much longer than our parents went to school. I know this is the case in my family. I'm the first one in my family to have graduated from college. My parents, my father in particular, had aspirations of doing that, but was never able to do it. And he used to ask me, what is it that you are studying? And I tried to explain to him. And one day I had that same experience that Jim described, that you described, Dr. Ganguly. And it's really it was a wonderful moment in my life as well. I mean, it's interesting to hear other people have that same feeling when that happens to them. It really is a nice feeling.
Cool.
I can.
See, Esteban had a question in the chat about the famous failed experiment. That was the Michaelson Morley experiment. Let me see if I can go back to that. Yes, no, okay. All right, work with me here. I think it's the laser pointer that's messing things up. Let me turn it off. So over here, the Michelson Morley experiment. So this experiment was a failure in the sense that they were looking for variations in the measured speed of light, and those tiny that would have indicated that we were in a frame that was different from what Maxwell, from the frame that Maxwell's predicted speed was in. Because they failed to find any differences that suggested that there is no particular frame that has that particular speed. And so that's what then led Einstein and others to then conclude that, hey, you know what? That speed must be true in any frame. So whatever frame you're in, if you're looking at light, you're going to measure that speed, that number, for light going through a vacuum.
Yeah, the speed of light's always the same. You don't need any ether.
Right. It precluded the need for an ether.
Other questions? Other questions?
Can you hear me?
Yep.
You can?
Yeah.
Oh. Okay. First of all, I really liked the outline of the speech. I thought it was really cool. Second of all, I really liked some of the questions. I had one myself. Third, do you know Randy Jacoby?
No, I don't.
Okay. I went to school with him and he was a professor at University of Arizona. That was a long time ago. I wondered how.
Okay, yeah. Those were the ancient times.
Number three, I have this toy where you spin this puck on a piece of glass and it goes round and round, and at the end it goes.
Mm-hmm.
You know what I'm talking about? I wish I could show it to you, but I don't know how to use this thing. And that, I don't know if I read it or it reminds me of the way the black hole ends. The way, it goes.
Okay. No, I can buy that. Yeah.
Yeah. Have you heard of that or?
No, I haven't. But that's interesting. I have to think about that.
Yeah, it just suddenly goes faster and faster and just quits.
Yeah.
And when you take two steel balls and you put them by your ear and you try to touch them once, you can't.
Yeah. There's that little bouncing effect. Yeah. Right.
Yeah. And it reminds me of how black holes, they must be, in some ways, like neutron stars, super hard. Would that be the right thing to say? Super hard?
Yeah.
Yeah, elastic. That's all I got. Thank you.
Yeah. That's interesting to think about. Yeah.
I like your speech.
Thank you.
Yeah.
Let me try to formulate a question if I can. When you see those waves that are generated by LIGO, those are reconstructed waves of the gravity wave caused by interference patterns between mirrors that reflect the laser light. So it's sort of a synthetic wave, if you will, I guess, because the wave.
Well, they are actually plotting what is the strain. That is, what is the change in the distance of the mirrors from the source. So they're detecting that very. I mean, it's extremely small. The units on that thing are extremely small. Let me see if I can go back to that.
Like 10 to the minus.
Those are actual measurements. Those are not just synthesized.
Okay. Okay, but it is a single dimension basically, and the gravity wave, just like an electromagnetic wave would have an E and an H field, this would have a physical dimension and a time dimension as well.
Right. Right.
Are we only seeing the physical dimension? Are we seeing a composite? Do we have to divide by the speed of light somewhere? You see what I'm getting at?
So in terms of translating the strain here into
what the wave looks like, yeah.
Right. So I mean, there's probably through calculating that has to be done in order to make use of this, in order to infer what's going on. Yeah. But they have made those predictions, and the predictions match pretty much right on with what was detected.
Mm-hmm.
The other aspect of that is that because of these detectors, let me see if I can go back to here. You notice that there's, you know, it is really in 2 dimensions. I don't know where this is coming from. Is that?
I did that accidentally, sorry.
Oh,
I was trying to work on the interface and I touched something.
I don't know. Okay, that's fine. No worries. So you notice that there are 2. So they can actually look at not just 1 dimension, but 2 dimensions. And so that's a useful thing. That's an important thing as well. So they have that in both Livingston and Hanford. So they can see what's going on both sides, both ends. And so as a wave comes through, they can see, you know, that also helps a little bit with the direction aspect of it as well. And where the wave is coming from.
Well,
yeah, I'm just a simple engineer. I can do vectors, but I can't do the tensor mathematics to relate.
You and me both.
I just can't.
I have a colleague that does all that for me. He's a very smart theorist that tells me how to do it. As I tell him, tensors make me tense. And stress tensors cause a lot of stress.
Well, with that, could I ask one kind of, well, a concluding general question?
Sure.
That was a rhetorical question.
Moderator's privilege.
You know, toward the end of your presentation, Professor Ganguly, you talked about all of the things that we have missed. There's certain urgency to investigate, to capture data, and that leads me to ask, going forward, well, the James Webb Telescope is supposed to go up in the fall, but what do we need?
Hopefully it does. It's been delayed so much.
Well, yeah, which fall?
Yeah, right.
What do we need in terms of new telescopes, new detectors? Where do we need to put scarce resources into new ways of capturing this data?
So for my money, what I would like to invest in more is in our ability to detect not just light, but also gravity waves. I mean, they've been doing things with Virgo now, combining the forces of LIGO and Virgo. So some of these additional things. There's also LIGO India coming up. So making things more sensitive in that way, but also improving technology. I mean, this thing was a fantastic technological achievement in just being able to damp out the noise sources, like over here, from this incredibly interesting, contraption where they're able to really damp out any noise sources. If there's a car driving along the road, along the side, that's going to create rumbling as well. They have to be able to distinguish, between those kinds of things and an actual signal, which is not going to be very strong. The strains here are on the order of 10 to the minus 21, which is incredibly small. So think of the strain as a relative change. So 1 part in 10 to the 21 is how it changes. So improving technology. I mean, the astronomy is very much a technology-driven field. So every time we've had an improvement in technology, we've had breakthroughs in seeing things. Every time we've expanded our horizons in being able to detect X-rays or radio waves or ultraviolet, or even gravity waves now. We have opened up a whole new way of looking at things, and we learn so much more just by doing that. So I would say, improving technology, that's where I would
How about
say invest your resources.
How about a third site in LIGO where you'd be able to triangulate from the source?
Right. So Virgo is allowing that to happen, and LIGO India is also coming online, hopefully soon. That will definitely help. So just having two, you only get a very crude estimation of this. I mean, there was a huge error bar on that contour map that I showed you at the beginning, that banana shape. But yeah, you can narrow those things down a lot. Yeah.
Well, very good. Thank you very much for that. I guess one last point, Timothy Thompson, you had a question about cosmological neutrinos. Did you jump in?
Well, you were asking him what do we need to expand, technology-wise? What kind of advances do we need to make? And obviously, neutrinos, especially if you can see neutrinos from the Big Bang or something, which can be behind the CMB and sneak up on you. But neutrinos, like gravitational waves, are really slippery. You don't just stick your finger up in the wind and catch neutrinos.
Yeah,
that's hard work.
Definitely.
So,
and even when we first started being able to detect neutrinos, we learned something profoundly important about the sun. Right? I mean, we figured out that hey, you know what? The neutrinos that we're getting, they're not the kinds of neutrinos that we are expecting to get from the sun, and that led us to a whole, new branch of physics regarding neutrino oscillations and the idea that neutrinos can change, their flavor, which is really cool. So you always learn something really interesting just by exploring.
The best part of that is that astrophysicists rarely get a chance to push the particle physicists around. And this time it was the solar neutrino problem that discovered neutrino oscillations. You have to take every advantage of those particle physicists you can get.
Absolutely. And even now with dark matter, trying to understand what it is, that's a joint venture with particle physics, trying to understand, hey, how does this fit within the standard model? Do we have to change the standard model in some way? I mean, standard models have been extremely successful in making predictions, but it's also a very ad hoc, sloppily put together model. So, there's things that we're going to learn now that we've isolated Higgs. The question is, where do we go from there? In order to understand how is gravity, do we have to revise the way we understand gravity working? Or is this the way gravity works and we have a different kind of particle that only interacts through gravity and not through other forces? This is all very interesting stuff. Yeah.
It'll be even more confusing if you discover that gravity doesn't have a particle, because it's the one theory now that you can't stick in the standard model. What if it just doesn't? What if you're stuck? Oh, well.
Right. On the theory side, what we really need is that quantum theory of gravity, understanding how does space-time behave and look on the very, very smallest scales. General relativity is great for large scales, but what happens when you go to those very, very small scales?
Well, with that, we're out almost an hour and a quarter, and I think very grateful for Professor Ganguly's time. Professor, thank you very much.
My pleasure.
Thank
you.
Thank you, Rajib.
Greatly appreciate it.
Thank you.
2 weeks from now.
Yep.
As we have mentioned.
Hopefully I did a good warm-up act for her.
Dr. Katie Bauman, who I guess had a very large role in that image of the hole that we saw. She will do a presentation on how that was done. titled Imaging the Unseen, taking the first picture
How do you
of
turn
a
this
black
on?
hole. That will be on March 13th at 11 o'clock Pacific time. And with that, also, thank you everybody for coming. I really appreciate it.
Thank you for having me.
Thank you.
And please,
Okay, great talk. Thank you.
please join us in 2 weeks.
Thank you.
And with that, I'm going to shut the session down.
Fair enough.
All right.
Bye-bye.